Good evening to one and all present here. I am Arundhati Mukherjee from Revered Media. We welcome you all to today's webinar on the topic From High Performance to Ultra High Performance Concrete. This webinar is organized by Indian Concrete Institute, New Delhi Center, in association with Civil Engineering and Construction Review, powered by Revered Media Private Limited. We would like to begin this webinar by welcoming Engineer Rajiv Singhal, who is the Chief Engineer in CPWD and Chairman, Indian Concrete Institute, New Delhi Center. We welcome you, sir.
Thank you. Thank you. Good afternoon, everybody. In the beginning, I would just like to give a brief of New Delhi Center. Just for the people who are not conversant with ICI, Indian Concrete Institute is a non-profit organization aiming to spread knowledge about concrete and to promote new technologies in the field of concrete construction. ICI New Delhi Center is one of the 44 centers of ICI and one of the older centers of ICI. ICI has total around 13,000 members and New Delhi Center has around 300. We are trying to increase our strength. I would request all the people who are not members of this center to kindly enroll themselves with ICI. Forms are available on the website of Indian Concrete Institute. And if there is any issue, you can contact me. Now, ICI New Delhi Center has been organizing a number of webinars. This series was started in the month of July, and we are holding webinars every Saturday now. In the month of September, New Delhi Center also celebrates Concrete Day, which commemorates the founding of Indian Concrete Institute on 7 September in 1982, around 4 decades back. Last year, we celebrated online Concrete Day in the month of September. And in the next month also, we plan to hold Concrete Day celebrations, and we'll keep you informed about the schedule. Last week, we had a webinar on high performance concrete. Today we are having a webinar on, this week we are having a webinar on ultra high performance concrete by Mr. P.N. Ojha, who is Joint Director Construction Development and Research in NCB Ballabgarh. And next week also we plan to hold a webinar in which speaker will be Mr. Supradeep Das, who is our Vice President North. Thank you.
Thank you, sir. Introducing to you all Engineer Supradeep Das, who is the current Vice President North, Indian Concrete Institute and Vice Chairman of BIS CED 41 Committee. Welcome you, sir. Sir, you're on mute.
It's fine now?
Yeah, we can hear you.
Thank you. It's a great pleasure to be present in the webinar series organized by ICI New Delhi Center. I welcome our National President, Engineer Vijay Guptaji, Rajiv Singhalji, Chairman ICI NDC, other Executive Committee members. I also welcome Engineer P.N. Ojha, our Speaker of the Day, along with Professor Bhattacharjee and Engineer Mayank Rawal, who are the eminent panelists for this evening. The topic itself is quite interesting. I hope that it will generate interest among the participants. As Vice President North, it's my responsibility to introduce ICI to the participants through a presentation, a small presentation, and which will give you an inside idea of the ICI and its activities.
Please share the screen.
I have shared the screen.
Yeah.
Okay.
Now we can. Yeah. Now.
So Indian Concrete Institute is in the service of promoting concrete and the related materials and construction. We have a new website that is called ICI Indian Concrete Institute.org. If you go through that website, you can share lot of information, can get lot of technical ideas, lot of developments which has been taken place in cement and concrete. It was founded in 1982 with in Chennai, where we have got around 44 centers. Midnapur was the latest. We have got 351 organizational member, 267 student members. Our objective is to promote growth on concrete construction and its sub-specialization, to disseminate knowledge and information, to identify R&D issues, train personnel, collaborate with national and international agencies, to collaborate with national and international agencies like American Concrete Institute, Singapore Concrete Institute, Concrete Institute of Australia, to arrange lecture series on selected topics of relevance to concrete construction from time to time. ICI also organizes periodical seminars, conferences, workshops, exhibitions, and subject of and arranges lecture series on selected topics. ICI publishes quarterly journals. ICI also has brought out number of publications, monographs. We also have an advisory service which offers an industry advisory service for problem solving in design, construction, maintenance, and repairs. We have its fold in the captains of construction industry, building materials, manufacturers, leading consultant, designers, civil engineers, construction chemical manufacturing companies, material testing laboratory, and students. So the knowledge is disseminated through the workshops, seminars, webinars, conferences, exhibitions, seminars, training programs, technical documents. We also have a technical committee on various aspects of the concrete and construction is there in ICI. Through them, we have published around 9 publications. The hard copies are available with the headquarter, or if you want a hard copy, you can check up with the vice president, chairman of the center, secretary, or the president. And for the soft, you can visit our website, indianconcreteinstitute.org. We have a joint initiative with government bodies like CPWD, BIS, BMTPC, state PWDs, IRC, CBRI, and others. We also have, by the side of the Centers Award, we also have ICI annual awards. Branded international events, ASECON, that is Asian Conference on Ecstasy, or celebrated once in 4 years, IWC, Innovative World of Concrete. These two are the unique platform in which experts from all over the world participate and share their experience. This year in 2020, the IWC was to be organized by the New Delhi Center, but somehow due to pandemic, now it has been postponed to 2021. The Concrete Day, as Mr. Rajiv Singhal has told you, that is celebrated all over the country by all the centers on 4th September. This is event commemorated with the formation of Indian Concrete Institute. We have a student chapters where the 50 student of a civil engineer can become a member and form a student chapter. In that case, at least 4 of the faculty members should be a member of the ICI. Our growth is undeterred, goals are high, targets are far-reaching. We remain committed to society at large and concrete lovers in particular. Thank you. But before going, I just would like to add, as you all know, that ICI NDC has collaborated with CE&CR and Revered Media for online physical events. The webinar today is second product of this association, and we propose to have a series of such events online and physical jointly in the coming days. I would now present CE&CR Revered Media to you all.
Thank you, sir.
And Construction Review, a leading infrastructure monthly on methods, materials, and machinery. Celebrating 34 years of publication. CE&CR is India's #1 infrastructure monthly news journal for the past 34 years. We have been providing discerning knowledge and an unmatched coverage of the construction sector since 1988. Get social with the largest online construction media network of India. Civil Engineering and Construction Review provides a valuable, informative, unmatched high-quality content. It is the most circulated magazine in India, having a readership over 17 countries worldwide. Google ranked number 1 under the search of Civil Engineering Magazine India and Construction Magazine India. We have a 5-star rating as well. Currently stands at 58,000 plus followers on Facebook. 16,500 plus industry professionals connected on LinkedIn. You can also find us on other social media platforms such as Twitter, YouTube, Instagram, and SoundCloud. No one around us in India. CE&CR has been awarded the prestigious Best News Magazine by CIDC in the year 2014 and 2019. Best Publication Award by the ACCEI in 1991. Designated for International Quality Summit Award in Gold category in Paris by BID in the year 2012. We cover topics such as roads and pavements, bridges, construction equipment, concreting, precast, high-rise structures, waterproofing, and many more. CE&CR is read by construction companies, contractors, builders, government departments, public sector undertakings, building material and equipment manufacturers, consultant and architectural engineers, research institutes, polytechnics, and colleges. Connect with the most circulated and trusted magazine in India.
Introducing Revered Media, a 360 degrees logistics solutions of business events. Who we are and what we do. Revered Media is an independent, full-service, professional logistics solutions company for business events. We specialize in corporate events with end-to-end event project management. Our commitment is to see each event through from the start to finish, while keeping the goals, vision, budget, and our clients' needs in mind at all times. We manage your events from conceptualization to execution, saving you the long hours, late nights, and endless emails so that you can focus on what's essential to you. We represent leading international exhibition organizers for promotion of their shows in India as well. Our unique selling proposition are: we have a focused and contemporary approach, wide contacts, rich experience in conceiving and managing high-profile events, working within deadlines and budget with maximum mileage and strong marketing instincts. We specialize in various types of events such as webinars, seminars, conferences, exhibitions, social media marketing, EDMs and e-newsletters, workshops, promotional advertisement and designing, public relations, product launch, award ceremonies, road shows, and many more. Our vision includes growth, innovation, affordability, and quality services. Contact us and join hands with Revered Media.
Now I would request Engineer Rajiv Singhal to introduce President ICI All India, Engineer Vinay Gupta, to the audience.
Okay, thank you. Mr. Vinay Gupta needs no introduction, but it's a formality to introduce him to all of you. And I am very grateful that he has joined us in this webinar. I know he's busy in another workshop on steel bridges, but out of his affection for New Delhi Center, he has taken out time from that workshop to join us. I am very grateful to him. Thank you, sir. Mr. Vinay Gupta is a graduate in civil engineering from BITS Pilani in the year 1983. He served with Span Consultants and Stoop Consultants before he joined TCPL in 1987, and he is presently working as Director and CEO of TCPL. He has vast experience in planning and design of bridges, flyovers, underpasses, tall buildings, steel structures, and chimneys, etc. He is an active member of various BIS and IRC committees for formulation of codes and standards concerned with designs of various bridges and flyovers and tall buildings, etc. He has published more than 50 papers in various reputed journals and a recipient of many awards. He is a visiting faculty in NITHE, CRRI, CIDC, ISDA, and some other institutes. He is also president of Indian Institute of Bridge Engineers, apart from president of Indian Concrete Institute. Thank you, sir. Now I would request you to kindly say some words of encouragement. So we can't hear you, sir. Kindly unmute.
Yeah, somebody muted me. I didn't know this. I said it's always a pleasure to attend any event of New Delhi Center of ICI. And of course, I have been the chairman there and thereafter Vice President North. And I must say, not because I have been the chairperson, but otherwise, that Delhi Center is a very vibrant center of ICI. Out of the 44 centers, one of the most vibrant centers, active centers, and full of enthusiastic set of people is New Delhi Center of Indian Concrete Institute. And of course, we have able people like Mr. Rajiv Singhal, who also happens to be Chief Engineer CPWD. We have co-chairman, Mr. Mayank Rawal, who again is so closely connected to concrete and its research. That is what is good about it. We have the Vice President, Mr. Supradeep Das. We have our Honorary Secretary, Dr. VVL Kanta Rao. Everybody is very closely associated with concrete. And of course, the structures. And of course, now out of the vibrancy that the center has, in order to make it further more fruitful, they have tied up with CE&CR, who have a long experience, you just now heard, and Revered Media for certain logistics. And of course, finally, we all partner. Partner means we are together. It's an affiliated event that we'll have. So Delhi Center started holding weekly events, if I'm not wrong, or rather very frequent events, let's call it. So this is the second one in the series, where it is again a coalition event with the CE&CR and Revered Media. But friends, on the other hand, let's also hear the not so good story. Delhi has a population of 1.5 crores. There must be not less than 3-4 lakhs of engineers here. But out of that, we have only 300 members. Even Nagpur, for that matter, has 600 members. Mumbai has in the range, Bangalore has somewhere in the range of 600 odd members. But Delhi has only 300. I think we must increase the strength. In fact, my dream had been to reach 15,000 from 13,000 or 12,700 that we have presently, which Mr. Rajiv Singhal said, members of ICI. And of course, from 44, we want to reach 50 centers at least in the next 1 or 2 years. The new centers in making will be Bidar, Tirupati, Jammu, Srinagar, Leh, etc. So we hope to add at least 6 more centers in the next 1 to 2 years, so that we reach half a century at least, which is a good landmark people want to achieve. Coming to cement. Cement was invented in Isle of Portland in England in 1824 by engineer Joseph Epstein, which is a synthetic admixture of clay and limestone resembling Portland stone. And of course, he took a patent also in 1824 on 21st October, which I'm sure most of you are well aware. But the interesting thing is, this poor Mr. Epstein may not have known that what all we will do with this cement. We are adding fly ash to it. We are adding blast furnace slag to this. We are adding admixture to it. And we are going one step further. We are creating high strength concrete, high performance concrete, ultra high performance concrete, and so on and so forth. So that is what we are eager to hear from Mr. O.P. Ojha, P.N. Ojha, that what all one can imagine doing with this simple cement or limestone material that we have in our country. We'll hear him. But before that, I must thank the able set of panelists. We have Dr. VVL Kanta Rao, we just heard just now. We have Professor B. Bhattacharjee from IIT Delhi. I hope he is listening. We have Mr. Mayank Rawal, who is a R&D specialist of construction chemical industry. So we have very able uh, our panelists here, and I'm sure they will be able to support Mr. Ojha very well. And with all these 4 people and the rest of the team, I'm very hopeful that the people will rejoice listening to the presentation today. Thank you so much and all the best to you.
Thank you. Thank you.
Thank you, sir. Now introducing our moderator for the day, Dr. VVL Kantarao. He is a senior principal scientist in Bridge Engineering and Structures Division, CSIR, CRRI, and Honorary Secretary of Indian Concrete Institute, New Delhi Center.
Thank you, Arundhati. It's my privilege to introduce. Good afternoon, all of you. This is our, you can say, third lecture in August, and the second under the aegis of Revered Media. It's my proud privilege to introduce our speaker, the P.N. Ojha ji. Mr. P.N. Ojha is a joint director and head of Center for Construction Development and Research in National Council for Cement and Building Materials, NCCBM, Balabgarh, Haryana. He is having more than 30 years of experience in the field of cement and concrete technology, new product development, high performance concrete, ultra high performance concrete, durability of concrete, structural assessment and rehabilitation of existing concrete structures, cathodic protection and reinforcement corrosion mitigation, geopolymer concrete, etc. He has published more than 60 research papers in various international and national journals, conferences and seminars. He is a member of 26 committees, panels and working groups of BIS, including a panel and working group responsible for the revision of IS 456. He is also the member of ISO panel of BIS on cement and concrete. Has been conferred Outstanding Concrete Technologist Award by ICI, Gurgaon for the year 2020. I welcome you, sir. Ojha, sir. Now it's my privilege to introduce our panelists, Professor Bhattacharjee. Dr. Bhattacharjee is a Emeritus professor at the Department of Civil Engineering, IIT Delhi. He obtained BTech honors degree from IIT Kharagpur, MTech and PhD degree from IIT Delhi. He worked for Gammon India Limited for 2 years after BTech. He is an nominated fellow of Indian Association of Structural Engineers and a member of several professional bodies such as ICI. He was involved with academic activities with several international institutions, namely EPFL Switzerland, University of Dundee, UK, etc. Also, University of Dresden, Germany, and Catholic University at Leuven, Belgium. He is involved with industry as a consultant and also in training. Professor Bhattacharjee has supervised 172 MTech and 26 PhD theses till date, and currently guiding 7 ongoing PhD research projects. He has published more than 180 papers in journals and conferences, etc. He is active in several national committees involving DST, CBRI, NCCBM, Dr. Fixit Laboratory, BIS, etc. A biography of Professor Bhattacharjee titled "A Teacher and a Research Worker" under the feature "People" is available in August 2012 issue of ICJ and also under title "Gems of Structural Engineering" in SEFI. A recipient of ICA Lifetime Achievement Award, North 2012, he acted as a member of editorial board of a magazine of concrete research, UK, and International Journal of 3 Hours. He is a guest editor of ICJ January 2015 issue on concrete research and also in 2019. I welcome Professor Bhattacharjee. He is going to join us very soon. He is busy in some lecture actually. Now, our second panelist is our own Mr. Mayank Rawal. He is the Director Technical of Messrs. Asian Laboratories. He did chemical engineering from IIT Delhi in 1977. Mr. Mayank Rawal is in the field of manufacturing construction chemicals for the past 35 years. He has been working in on high performance concrete using 4th generation superprocessors, VMA, etc. Mr. Rawal has done specialization in the chemical grouting of dams, tunnels, etc. and was a technical advisor for the Tamil Nadu Electricity Board, Gujarat Electricity Board, Karnataka Power Corporation Limited, Northeastern Power Corporation, etc. He has written several technical papers on the performance of concrete in national and international conferences. Mr. Rawal is actively associated with the ICA local chapter of New Delhi and is presently Vice Chairman of ICA New Delhi Center. He has been actively organizing international national conferences and workshops etc. Mr. Rawal is also a member of ICI Technical Committee 03, the Technical Committee on Concrete Admixtures. With this, I welcome Mr. Mayank Rawalji. Now I invite Mr. Ojha sir to deliver his lecture, please. Sir, please unmute कीजिए and share your screen. Yes, sir, it's visible, sir. You are not audible, sir. Please unmute yourself.
Am I audible?
Yes, sir. Now you are audible.
Okay, okay. Thank you very much. So this topic which I discussed with Singhal Saab. So thank you very much for ICI, everyone, ICI President, Vice President, Kanta Raoji, and my Guru, Dr. Bhattacharjee, Mayank Rawalji, and everyone from ICI. So giving me the opportunity to discuss with such a august gathering on this topic, high performance to ultra high performance concrete. So the four aspects we will be discussing: optimization, design, performance, and application. So the agenda will be from ordinary concrete to ultra high performance concrete. There is a gradual change in material selection, mixed design approach, concrete property, performance, production, microstructure. So we will see how and why the gradual changes has taken place. Then we will be discussing the challenges in widespread implementation of UHPC. Then some application of UHPC world over we will see. Then we will discuss optimization and design of UHPC through a case study with work which has been done at NCCBM, and then we will conclude. So with this agenda, now we know we have three groups of concrete in our existing IS 456. Ordinary concrete up to M20, standard concrete from M25 to M60, and highest strength concrete, now concrete up to M100 has been added. And according to the changes in the material property, a little bit we will be discussing how the things have been added or being planned to be added in the revision of IS 456. Then we aspire to add in future very high strength concrete in the range of M100 to M50. And we also aspire to add in the future in IS 456 ultra high strength concrete. Mainly the world knows when the concrete strength has more than 150 MPa. Apart from other performances we will be discussing today. So concrete from production process, properties and performance, how gradually it is changing from ordinary concrete to ultra high strength concrete. So production process. So production and process, from theoretical principle of production of concrete, we are also changing, because when we are getting the concrete from M20 to more than more than 150 MPa. So in standard concrete or like so, only the water cement ratio. So higher the water cement ratio, lower the strength of concrete, and lower the water cement ratio, higher the strength of concrete. This is the principle. And we are selecting the well-graded fine aggregate and coarse aggregate together. But when going to the high strength concrete, we started looking at the other aspects also, the packing, the ultra fine materials, use of ultra fine materials like silica fume and ultra fine other cementitious material like ultra fine GGBS. When coming to the very high strength concrete and ultra high strength concrete, we started looking at the packing density, how to reduce the combined porosity like that. And if we see the water cement ratio, the water cement ratio, when we are coming to the ultra high strength concrete, we need to work in the range of 0.14 to 0.2 water cement ratio. And we need to get the concrete workable, and without having a very good super plasticizer, we cannot achieve it. So the raw material selection also becomes very, very important. In earlier standard concrete, we were not thinking of the quality of aggregate, but as gradually we are increasing, we are also thinking the quality of aggregate. Not only that, the size of aggregate. So the raw material selection becomes important gradually when we are increasing. The mixed design approach, as we said, is also different a little bit. Then mixing method also. A same mixing method to get the concrete is not with the standard concrete and very high strength concrete or ultra high strength concrete. And the curing regime has become very, very important when we are discussing the very high strength concrete or ultra high strength concrete. We will be discussing it. But why we are doing it? We are doing it to get some properties. So concrete properties and performance, and we somehow and by some means we are affecting a different way of hydration, a different way of getting the fresh concrete properties, and in doing so we are getting a different microstructure, a little bit different from the ordinary concrete. Then how the mechanical properties are changing. Some properties are in positive direction, but improvement in one property at the same time causes impairment of another property. And how we are taking care of as a civil engineer or as a researcher, that will be discussing. Mainly the strength and mainly stress-strain relationship, its toughness and impact resistance is also changing. And dimensional stability is one of the problems, like shrinkage and cracking resistance. It is also changing gradually. And of course, durability property. So this is the gradual change which we are going to discuss a little bit. But we can see the microstructure development. Whatever we are doing and whatever we are adding and whatever we are getting, we are developing some microstructure. Because of that, we are getting some properties out of concrete. So microstructure has a great influence on concrete property. Not only one property, but it affects the mechanical property, transport property, which affects the durability property thereby, and then volume stability also. So we can see by the schematic diagram, an aggregate and a bulk cement paste is connected, and in between, we call it the interfacial transition. And this interfacial transition zone, when the water cement ratio is high, it's very, very thick, very, very wide. And wider the interfacial transition zone, lower is the strength. Not only that, if we will see, we can see from the schematic diagram CHS gel and calcium hydroxide and anthracite. Most of the calcium hydroxide and anthracite are in the interfacial transition zone. And because the water cement ratio is higher a little bit in relatively, so they are oriented towards the aggregate while producing the concrete. And this is the weakest zone, and most of the time it's affects the performance of concrete. And when this is interconnected, it affects the permeability of concrete, transport properties of concrete, and thereby durability of concrete. And we can see at 0.5 water cement ratio, what is in the right side, what is the coefficient of permeability, and at 0.2 in nearly to the zero, the coefficient of permeability is nearly to the zero. When we are working below 0.2 water cement ratio, this is the ultra high performance concrete. And if we see the ACM image, the ITZ in conventional mortar at left side and ITZ in ultra high performance concrete mortar in right side. So the interfacial transition zone has high porosity and calcium hydroxide content in the conventional concrete. We can see a canal like gap between the mortar and fine aggregate. However, going to the low water cement ratio, particularly below 0.2, and pozzolanic reaction between the calcium hydroxide, whatever is being generated, it is being used by the reactive mineral admixture, which consumes whatever the CH crystal, means calcium hydroxide crystal, is getting generated. It is getting converted into CHS gel. So additional calcium hydroxide is not available in the interfacial transition zone, and therefore the interfacial transition zone in ultra high performance concrete seems as dense as the matrix. So this is as dense as matrix is the homogeneity across the microstructure components. And the CHS gel in ultra high performance concrete has high density, means the quality of CHS is also different. It has a high density characterized by intrinsic higher stiffness and hardness. So the CHS gel in the UHPC has higher stiffness and higher hardness than those of low density CHS that dominates in conventional concrete. So in conventional concrete, we get low density CHS, but in ultra high performance concrete, we get high density CHS. And this is also the reason in the changes in property. So we can see, as we have seen from the schematic diagram and discussing through the ITJ, we can see a schematic diagram, the time dependent phase development in ordinary concrete and ultra high performance concrete. The intrinsic, the volume of intrinsic is very, very low. We can see the portlandite at the bottom of the both of the portlandite is the calcium hydroxide. The volume of portlandite is very, very low. So intrinsic as well as portlandite, which is available in the ITZ, is real availability is very, very low. And in ultra high performance concrete, we reduce the aggregate size also. And by reducing the aggregate size, that decreases the probability of its own defect. So whatever the defects in aggregate, and because of that, inhomogeneity is created, that is also reduced because of the reduction in aggregate size, and thereby reducing the inhomogeneity of concrete. So reduction of aggregate reduces the inhomogeneity in the concrete of UHPC. So how the mechanical property changes, and which is being incorporated in IS 456 right now, we have discussed, and almost the draft is getting ready. The single idealized stress strain curve in existing IS 456 is available, and which is applicable for the grade M15 grade. But we see in the right side of graph, the nature of stress strain curve is changing when we are increasing from M20 to M100, and in ultra high performance concrete it will further change, which we'll be discussing in our case study. So with these changes, the corresponding changes in IS 456 is also being incorporated. So we can see the stress strain curve of M100 grade of concrete is more steep. And because of this, we can see the maximum stress strain and strain at peak stress. The both are different from M20 grade of concrete to M100 grade of concrete. At M100 grade of concrete, both are becoming closer, like 0.00240 and 0.00240. And in M20, it was different. So this aspect is being taken care in the revision of IS 456, and this table will be made available there. But while going to the from lower strength to higher strength, highest strength concrete, and then to very high strength concrete, and then to ultra high strength concrete, with many advantages, there comes some disadvantage also. So the concrete is becoming more brittle behavior. It is having low strain capacity and low fracture toughness. The second aspect is it is getting poor fire resistance property and lower spalling resistance under fire. So how to tackle these two disadvantages for our sake of advantages. So concrete, we can see a typical quasi-brittle material with low tensile strength, strain capacity, and fracture toughness. We can see from the picture. So use of steel fiber, we can see in the picture of right side, is a viable solution to modify post-peak behavior. Not before that, a post-peak behavior is affected when we add the steel fibers. So to modify the post-peak behavior of stress strain curve of high strength concrete or very high strength concrete and thereby ultra high strength concrete also, to have some degree of ductile behavior, we can add some fibers. And how the fiber works, we can see from the left side of the picture how the addition of fiber affects the fiber matrix and debonding between the concrete and fiber, then fiber breaching, then fiber pull out, and then fiber failure. And energy absorbing mechanism of fiber matrix has been given in this picture. And a typical tensile strain softening and hardening behavior of FRC is being depicted here. And when we add fiber, there is a multiple cracking and localization, and because of that, it has a higher energy absorption capacity. So how to address incoming deficiency with increasing strength of concrete? We can add the tensile strength of ultra high performance concrete, ultra high performance fiber reinforced concrete. We have seen that it linearly increased with increasing fiber volume from 0 to 5%. But 5% addition of fiber is having a problem while mixing. So in order to minimize the amount of fibers and achieve desired tensile and flexural performance, combination of micro and macro fibers are being used. And UHPFRC with twisted macrofiber shows very good tensile performance with respect to post-cracking strength, strain capacity, and multiple micro-cracking behavior. It also shows that the very good tensile performance, not only tensile performance, but flexural performance also. I have written it down wrongly. It also shows very good flexural performance also, apart from tensile performance. Now come to the second aspect, fire resistance of high strength concrete. So high strength concrete, because of thermal stresses during the fire and because of the increased pore pressure, it expels, and there is a problem with the fire resistance property. So to take care of this, so we are discussing in the IS 456. But let us see the spalling resistance of the concrete at elevated temperature significantly improves by addition of polypropylene fiber. Addition of polypropylene fiber doesn't affect much the mechanical property, it has been established, but it affects this spalling resistance against fire. So therefore, the use of polypropylene fiber is a viable solution to modify the behavior of high strength concrete and the very high strength concrete and ultra high strength concrete also. So we can see the melting of PP fibers in concrete happens at 170 degrees centigrade, and it leaves a space to accommodate that the pore pressure. And right side we can see the physically the fire resistant performance of concrete with PP fibers, right side and left side. So the addition of PP fibers, because of the melting of PP fibers at 170 degrees centigrade within concrete, increases the permeability of concrete and releases the high pore pressure. And because of this, we are discussing, and we have almost concluded, but anyway, the comments will be there while wide circulation. So to avoid the spalling in high strength concrete, when concrete ranges in between M60 to M75, explosive spalling shall be avoided, and falling of concrete in the later stage of fire exposure shall also be avoided, and that can be avoided with the inclusion of at least 1.5 kg per cubic meter of monofilament polypropylene fiber. When the maximum, and this happens with the addition of silica fume. So silica fume addition makes the concrete more vulnerable against fire. So when the silica fume is less than 8%, this is recommended that 1.5 kg per cubic meter of concrete polypropylene fiber shall be added. But when the concrete is over and above M75 grade up to M90 grade, and the silica fume is more than 8%, then at least 3 kg per cubic meter of monofilament propylene fiber should be added. And when the concrete is in between M90 to M100, which is going to exist in the IS 456, then either of the three methods, a reinforcement mesh with nominal cover of 15 mm. This mesh should have a wire with a diameter more than 2 mm with a pitch 50 by 50 mm. The nominal cover to the reinforcement should be more than 40 mm. A protective layer for which it is demonstrated that no spoiling of concrete occurs under fire can also be adopted. And it can be included in the concrete mix more than 4 kg per cubic meter of monofilament propylene fiber. And this can also be, similarly, with more research, this can be the one of the measures when the fire resistance property of ultra high performance concrete will be debated, discussed, and researched. So what is the UHPC? It's a combination of the three technology: the self-compacting concrete, the fiber-enforced concrete, and high-performance concrete. So ultra-high performance fiber-enforced concrete. And there is a so many advantages of having this technology. So by definition, ultra-high performance concrete can be defined as a cementitious-based composite materials with compressive strength over and above 150 MPa, and thereby enhanced durability via their discontinuous core structure. But due to this, the ultra-high strength and high ductility, the application of UHPC may result into lower life cycle cost due to longer service life because of the enhanced durability. And various names by the more or less similar, the various name of ultra-high performance concrete is existing in the literatures. Sometimes ultra-high performance mortar, sometimes densified with small particles, DSP, sometimes FRHPC, sometimes high performance fiber enforced cement composites, sometimes the people call it micro defect free concrete, multi-scale fiber enforced concrete, or reactive powder concrete, also steel fiber cement based composites, or ultra high performance concrete. So more or less the similar things, a little bit variation, a little bit difference. So more or less these are the names, and technology is mostly same. So how we are selecting the materials? We can see the conventional concrete, the particle size distribution, the high strength and high performance concrete, the particle size distribution and specific surface area, and nano-engineered concrete. This is also one of the name of ultra high performance concrete we can thought of. So nano-engineered concrete. So we have a wide range of materials of various particle sizes, and to have them to get a close packing density is the process by which we design the ultra high performance concrete, and we select the material. So let us discuss the second aspect, what are the challenges in getting this technology readily implementable or readily implement everywhere. So we have still there are a lack of international standard design codes and guidelines. This technology or this concrete has a high initial cost and high energy consumption. Then high quality control is required. That is very, very difficult to maintain at site. And number of concrete technologists, engineers, and experts in UHPC is also limited. So it is our duty from the ICI to increase these numbers. So recently, the 3 standards is available from France. The one is NFP 18470, and it discusses about the specification, performance, and production and compliance of UHP FRC. The second one, NFP 18710, discusses about the design of concrete structures, specific rules for ultra-high performance fiber and forced concrete. And third one, NFP 18451, discusses about the execution of concrete structures, specific rules for UHP FRC. And the earlier to this, there were the published documents, technical guidelines and professional recommendation generally used in designing UHPC, but these documents has replaced them. And before these standards were developed, several other French, German, and Japanese recommendations were referred. So now, slowly and slowly at international level and in future at national level also, we will be having the standards and guidelines available with us. So what are the recommendations in this NFP 18470 from performance point of view? So maximum aggregate size, they have recommended that it should be less than 10 mm. The concrete density like this 2200 to 2800 kg per cubic meter. Tensile strength more than 6 MPa. In actual cases, it is much more than this. The water porosity at 90 days less than 9%. In actual cases, it is much less than this. The diffusion coefficient, polarized diffusion coefficient, less than 0.5 into 10 to the power minus 12 meter square per second. And then apparent gas permeability at 90 days less than 9 into 10 to the power minus 19 meter square. In actual cases, both these values are much less in case of UHPC. So application of UHPC, because of the excellent performance of UHPC, it offers new opportunity for infrastructure works like building construction, many other niche market with increasing number of application, which we have seen in the recent years in various countries like Australia, New Zealand, Canada, USA, Germany, France, Italy, and Japan. And how the market of UHPC is growing, one agency has surveyed, and it says that UHPC global market size is valued to $892 million in 2016, and they have predicted that it is going to grow by $1867.3 million in 2025. So this is a growing area. So the first structure using UHPC was made in Canada, Sherbrooke, and it was having 200 MPa, and we can see this bridge top and bottom chord members has used 200 MPa concrete, and the span was 60 meter. Now the second road bridge in France in 2001 having 180 MPa concrete, 90% reduction on steel reinforcement, main steel reinforcement, lighter structure with 60% weight reduction than conventional concrete. And from opening to traffic from 2002, there is no significant maintenance operation had been done. Now third one is in Korea, the year 2004, arc bridge with reduced segment. Construction methodology is pre-cast, pre-stressing with post-set heat treatment, and compressing strength of UHPC reinforced with fibers 180 MPa. The fact is, the total volume of UHPC 120 meter cube, having self-compacting in nature, and 12 tons of pre-stressing steel was used, but no conventional reinforcement was used in it. How the segments were cast, how the erections were done, we can see from this photographs which had been taken from the websites. Another example is Foundation Louis Vuitton in France. This is a modern contemporary art center and museum. The cladding and sheets of UHPC, so 19,000 cladding and sheets of UHPC has been used, and those UHPC was having 180 MPa strength, and it has been envisaged that it will sustain for 100 years. In Canada, again, light rail transit station. It has only 20 mm thick, thin-celled precast ultra-high performance fiber and post concrete roofs. And compressive strength ranges 150 MPa, and flexural strength was in the range of 18 MPa because fiber was added. And advantage is it has a little maintenance, lightweight, and easy construction because it's a precast component. In Paris, a stadium has been built. So roof and facades, the compressive strength of 150 MPa and flexural strength having 18 MPa was again used. In some cases, in this again 200 MPa concrete was also used. So what is the advantage? Advantage is precast UHPC elements, waterproof roof and facades, cylinder structure with unique design. And some of the bridges, again in USA, like in Iowa, again in Virginia, again in Iowa, and again in another place also. So, and so many bridges in USA is being rehabilitated and replaced using this ultra high performance concrete technology. So with this background, how we should optimize and design, what is the theoretical principle behind the optimization and design of this UHPC. So this is the 5 basic principle in designing UHPC. Minimizing the composite porosity by optimizing the granular mixture through a wide distribution of powder size classes, because we have a cementitious powders, cement and cementitious powders, wide variety. So we shall use judiciously in a proportion, and reducing the water binder ratio, because unless otherwise we will choose across the wide distribution and wide particle size distribution, we cannot reduce this water cement ratio. Then second theoretical principle is enhancement of microstructure by post-set heat treatment to speed up the pozzolanic reaction of silica fume and other ultra-fine materials, to increase the mechanical property, particularly modifying the ITJ, and optimal usage of super plasticizer to reduce this water cement ratio and improve workability, because most of the time we need a self-compacting nature of UHPC. And the fourth one is improvement of homogeneity. This is done by eliminating the coarse aggregate, resulting in decrease in mechanical effects of heterogeneity. And whatever the deficiency is generating out of this in terms of the brittle behavior, the improvement in ductile behavior by adding adequate volume of fraction of small steel fibers. So how we optimize the whole mixture? So that there are the 3 principles. It is being debated in the research arena. The broad area is ideal curves. It's a group of particles with a specific particle size distribution are combined in such a way that the total particle size distribution of the mixture is closest to the optimum curve. So we get a optimum, we get an ideal curve, and with combination of our design, we try to match with the ideal curve, and the maximum possible is called the optimum. Then second is the particle packing models is being used, and the third one is discrete element model also. So this 3 basically, but the purpose of the three lot seems to be the same. So these are the mixed design approaches, the ideal curve, the particle packing models, and with little variations, there are different models are also available given by some research, different researchers. But we have at NCCBM adopted this ideal curve method and this particularly modified Anderson and Anderson method, and which we'll be discussing in detail. Apart from that, we are also combining with the particle packing model also by calculating the wet packing model also. So we have used the two methods in a combined way, which we'll be discussing. So optimization curve, this curve, which is well known and given by Fuller and Thompson in 1907, this is the basic principle behind whatever we are doing in designing of conventional concrete, and that's why fine aggregate and the coarse aggregate is 2 times of the fine aggregate, because in this Q distribution modulus is equal to 0.5, but this is the modified one. So this modified one in 1930 was given by 1997 almost, was given by modified Anderson and Anderson, and this equation where PD is the fraction of total solid being smaller than size D. And why this has been given? Because it is essential to have a minimum size and maximum size, and only then we can optimize. Then and D max and D minimum is the maximum and minimum particle size, and Q is the distribution modulus, and the Q more than 0.5 leads to coarser concrete mixture, like ordinary concrete or conventional concrete in the range of M30 or M35, like that. Sorry. But where we adopt the Q less than 0.25, we can go the concrete mix having a strength even more than 250 or like that. In our case, we have adopted in between 0.37 or like that, and we want to go lower and lower distribution modulus in the future also. So the lower value of distribution modulus results in concrete mixes which are rich in fine particles. And procedure to optimize further is there should be the individual particle size distribution demonstration for each material. Then we should combine particle size distribution. So combining them, we should combine for the different combination and calculate on the basis of the fraction of material in the mix. This should be done separately for the cementitious material, and this should be done separately for the aggregate. Then deviation of grading of these combinations from the optimum grading curve as per this modified method shall be calculated using least square method. Combination with least deviation shall be selected for further investigation. How it can be like this? So this lower curve is the ideal curve, and the upper one is the combination which has been designed, and the minimum is the gap, better is the combination which is being adopted. And the proportion of each individual material in the mix are adjusted until an optimum fit between the composed mix, which is going to be tried, and the target curve is reached. And this is an optimization algorithm based on this LSM and as presented here. And when the deviation between the target curve and the composed mix is minimum, and it is assessed by the sum of the square of the residual RSS, then it's a better mix. But when we have optimized this mix, this is the optimization based on dry density. So this mixer design is often carried out through software based on the design dry density. Usually it is done in software and MATLAB. We have done through Excel. If we will be doing through the software and MATLAB, the combinations will be far better and far better optimized. But this dry mix, based on the dry packing density, we should further obtain mixer proportion of UHPC verified by the experiment in terms of wet density. So the packing density and optimal water film thickness and the paste film thickness for optimization becomes very important. As I was discussing that we have adopted the combination of the two to get the better results. And what is the packing density? It is defined as the volume of solids in a unit volume. And more is the value, better is the optimization. And the water film thickness and paste film thickness is very important. So we will see the excess water film thickness is not good. It reduces the strength. Excess paste film thickness is not good. It reduces the strength and other property. So optimization, and if we reduce it very low, then we may not get the workability. So calculation of the water film thickness and paste film thickness, and of course mortar film thickness when we are designing the high performance concrete, because high performance concrete is having coarse aggregate also. And this optimization of water film thickness and paste film thickness from point of view of getting better strength and from point of view of getting better workability, the optimum is required. And the wet packing density, because there are beneficial effects of water and super plasticizer on the packing density, and because this mixer has a more powder content, so it is better to get the wet density. And wet density by having count the water component also, we can calculate like this. So BC is calculated with this formulae, and where BC is the solid volume of the cementitious material, and the wet packing density phi can be worked out by VC divided by total volume V. This wet density, if we can see in combination of the two, the higher is the wet density, better is the strength development. So normal strength concrete is having wet density in the range of 0.65 to 0.72 if we calculate it. The high strength concrete is having wet density 0.72 to 0.8. But for ultra high performance concrete or ultra high strength concrete, we need to have the wet density more than 0.8. And we can see the higher the packing density, more is the compressive strength. We can see the water film thickness. Higher is this water film thickness, less is the strength, and that's why there is an optimum required. We can see the paste film thickness. The higher is the paste film thickness, less is the strength, and that's why its optimum is also required. Apart from this, the curing regime, as I discussed, the curing regime of ultra high performance concrete, unlike in other concrete, is very important. And why it is important? From the literature, it has been found that curing at elevated temperature increases the hydration rate, accelerates the rapid formation of hydration products, resulting not only higher early strength, but also high ultimate strength. So when we are doing the steam curing or elevated temperature curing for normal strength concrete, ultimate strength is lower. The strength development in initial strength is higher, but ultimate strength is lower. But in case of ultra high strength concrete, ultimate strength is significant margin higher in comparison to the curing at ambient temperature. So result of the ultra high performance concrete at elevated curing temperature is in contrary to the results obtained for normal strength concrete. And this one of the researcher has found that the 24 hours steam curing, there is a gain of 15 to 20 MPa compressive strength over and above the curing at ambient temperature. And similar is the case in autoclave curing, which shows more attractive strength enhancement than steam curing. So there is a 3 curing regime being advocated and being used. And in the earlier application area, in most of them, while preparing and while executing, the precast component has been cured at elevated temperature. So this is a standard room temperature curing, which is most common, economical and environmental friendly. But researcher says that CHS chain length is very, very short in this case out of hydration, and pozzolanic activity is also weak, and therefore strength development is not as much as at elevated temperature. Second one is heat curing under atmospheric pressure. So it is a better proposition. Flexural strength is also improves and compressive strength also improved. And why it is? Because this is due to the increased chain length of CHS and increased pozzolanic reaction. At high pressure steam curing, autoclave curing, again the compressive strength and flexural performance is further increased and further improved over and above the elevated temperature curing at ambient temperature also. And this is also due to the further increase in chain length of CHS and increase in pozzolanic reaction and pozzolanic activity. But curing regime also affects the shrinkage and creep of ultra high performance concrete, and this is a wide open area of research. So very, very limited studies has been conducted in this area. And how we do it, as we do for the railway sleepers and in any so at elevated temperature curing, not in autoclave, this is done in a stepped manner, like delayed period, then heating, then controlled heating and keeping the same temperature, then controlled cooling, and then keeping the members in the air. So what the studies we have carried out at NCB, I am going to discuss now. We have also published a paper recently in 2020 in Journal of Asian Concrete Federation. So we took a research paper on development of ultra high performance concrete, and the aim of the project is to develop the standard guideline for material selection, mix proportioning and procedure, deciding about the curing regime, and deciding about the design parameters, structural design parameters, as we have done for in case of high performance concrete, which has been incorporated in being incorporated in IS 456, which is being recently revised. So we would like to do that in advance for the very high strength concrete and ultra high strength concrete also. So studies on various mechanical and durability properties is also being done, and some studies we have completed. So we took the wide range of cementitious material like silica fume, nano silica, ultrafine slag, fly ash, and GGBS and OPC, and we determined the particle size distribution individual. Then we took the fine and coarse quartz sand and ground quartz as an aggregate, and we also determined the particle size distribution of the aggregates. And then we also took the high range water reducer, which was used in combination for developing this UHPs. So this is the properties of cement, OPC, fly ash, GGBS, silica fume, ultrafine GGBS like this. And we can see here the blend fineness and the fineness obtained from BT method for silica fume and ultra fine GGBS. So we have taken a wide range of wide range of particle size distribution and which can be interpreted from the blend fineness for production of ultra high performance concrete as far as cement and cementitious product is concerned. And combination of them have provided us the wide range of particle size distribution. So wider range of particle size distribution reduces the at the same workability, reduces the water demand, and this principle has been kept in mind while selecting these materials. Then we have different combinations with different cementitious material. We are theoretically optimized. So hundreds of combinations have been optimized. If it would have been MATLAB, we could have analyzed thousands and thousands of combinations, but we had a limitation. We did it from the Excel. So hundreds of combinations were analyzed and theoretically optimized for optimum particle packing with the help of this method. And after that, we come out with the three, PM1, PM2, and PM3. This is the mix number. And after optimization, we derived the RSS value, and it is having 418, 417, and 318. And we can see the 318, we perceive that it is out of the three, it is the best one. And the combinations having RSS more than 418 were rejected for this study. And out of this, when we decided this is the detail of mixed design, binder content, total binder content, 1000, water binder ratio 0.17. The nano silica was used. It was not taken in the optimization. Nano silica was used 3%, and admixture dosage PC based, very good PC based admixture 2%, and the coarse quartz sand, fine quartz sand, and ground quartz were taken in the ratio of 30 to 40 to 30, and this was also optimized on the same basis. And this is the whole particle size distribution, whole mixed design components. Then we can see when we determine the wet density, the packing density of all three mixes was found to be more than 0.8. For mix PM3, the value of packing density was highest among all the three mixes. While determining the particle size distribution of silica fume, it was found that it is very difficult to determine the particle size distribution of silica fume which we are going to use, because the particle size distribution of ultra fine materials like silica fume shows erroneous results because of its agglomeration nature, agglomeration into clusters. And external sonication is required to break down these agglomerations. And in our study, we found 5 minutes duration of sonication as an optimum time to break the agglomeration. And we can note that over sonication or under sonication. So when over sonication beyond a particular duration may lead to re-agglomeration of individual particles. So optimum time of sonication is also needed. So this right side curve shows like this. So when we optimize the mixture and we went to the laboratory to mix them in a conventional mixture, we had a lot of problems. So the two basic problems was because this mixture was having a low water binder ratio and high powder content. So there was a ball formation. It was not getting a homogeneous mix. Till the time it was getting mixed, there were the balls formed. So we at all. And the second, while mixing time was more, we were getting the air content introduced in it. So we gone through the literature, we gone through the other areas of other literature. Then we found that we need to design the mix which has a high efficiency. So we developed with the Emil. Emil is an equipment supplier. So with the help of Emil, we developed a planetary mixer for our laboratory having high mixing efficiency. And this helped in producing homogeneous mix with high powder content and low water binder ratio. And this mixture was able to have, produce low speed in between 0 to 125 RPM, then medium speed, and then high speed at 250 to 325 RPM. And this was the mixing sequence: drying mixing of all the cementitious material and aggregate at low speed for 3 minutes, then adding 100% water and 75% super plasticizer at 250 RPM for next 5 minutes, then adding remaining super plasticizer and mix the constituents at 325 for next 5 minutes, and then mixing them. Mixing continues until the concrete achieves the required flow. And we adopted the 3 curing regime: autoclave curing regime, steam curing regime, and standard water curing regime for all the 3 mixes. And we can see the steam curing regime elevated, the samples were kept at elevated platform in curing tank for steam curing. Then what we found, the compressive strength, this is the matrix from normal curing, steam curing, and autoclave curing versus PM1, PM2, PM3. And we can see the PM3, which was having least RSS value, and in autoclave curing for 5 hours, we got the maximum strength versus this. So maximum compressive strength of 186 was achieved, and the mix was having 60% OPC, cement, out of cementitious content, 6% OPC, 10% silica fume, 20% fly ash, and 10% ultra fine GGBS. And we can see from this graph also. So we determined the modulus of elasticity on cylindrical samples of 100 mm by 200 mm. And we also determined the Poisson's ratio in our laboratory. And we find that modulus of elasticity and Poisson's value like this. And when we compared the conventional, normal, and high strength concrete, UHPC has higher strength, not only higher strength, but higher modulus of elasticity also. And this was validated by the results too. As the strength of concrete increases, the modulus of elasticity also increases. And this is in case of UHPC also. And why this is? Because the UHPC has a greater stiffness of mortar constituents and the higher matrix aggregate tensile bond strength, particularly in ITJ. And this has caused an observed increase in the modulus of elasticity. So we determined the split tensile strength also, and it came 7 to 9% of compressive strength. And we know from the literature that for normal strength concrete, the split tensile strength is almost 10% of the compressive strength. And as the strength is higher, this percentage goes down. And in this case of UHPC, it was in the range of 7 to 9%. So stress strain curve was further steep in comparison to high performance concrete or high strength concrete in case of UHPC. So this is the stress strain curve corresponding to the PM3. And these 3 figures gives the stress strain characteristic of UHPC with respect to cylindrical compressive strength in the range of this. But the point is to be noted that the strain at peak stress and ultimate strain obtained was in the range of 2095 micron and 2204 micron. And we can note that this strain value in the case of high strength concrete is 2600 micron. So 2500 to 2600. So this is further low in case of UHPC. And what it shows that more packed structure of concrete matrix with low deformable upon application of load. And the absence of post-peak response can be attributed to the brittleness of UHPC. And this brittleness is taken care by addition of microfiber, steel fiber, and to some macrofiber also, as we have already discussed. So porosity, so to get the idea about the microstructure further about the porosity and pore size distribution, we determined the porosity and pore size distribution out of the concrete elements taken from the concrete cube, and we determined it in the mercury intrusion porosimeter, which is available in our laboratory, and we find the porosity very, very low in comparison to the conventional concrete and even high strength concrete. So what is our conclusion? We adopted the distribution modulus Q as 0.37. If we would have been adopted in the range of 0.25 or 0.23, the results would have been further better. The weight density for all the three mixes was more than 0.8, and if we would have again adopted Q value in the range of 0.20, this weight density would have further improved. The mixing methodology and type of mixer is very, very important. Whether we are producing it in laboratory, similar things will happen in the at a casting yard, where we can adopt this technology in real life situation. And planetary mixture is required for this to enhance the efficiency, because we would like to mix the components at a different RPM during the course of mixing. The post-heat treatment enhances the microstructure of concrete, and therefore we can thought of that this kind of technology, because of the better quality control and this post-heat treatment requirement, it is better to have the component in precast environment. So in situ concrete construction, for in situ concrete construction, there is not a right methodology. From the results, we can see that 186.5 MPa in case of autoclave curing we obtained, and when this is the conventional normal and high strength concrete, UHPC has a high strength, high modulus of elasticity. Strain value we have discussed. So this is my last slide. What is the guidelines in nutshell? It is not elaborated. The optimization of particle packing using ideal curve method. Select the material. Material selection shall be done in such a way to achieve higher packing density by selecting the material having high range of fineness. Planetary mixture should be used to achieve high mixing efficiency. Adopt appropriate mixing methodology to achieve uniform mixing. And the fifth one is appropriate curing regime, particularly heat curing or autoclave curing is required. So thank you from my side. Thank you very much. Thank you ISI, and thank you all the members of ICI for giving this the opportunity to discuss my thoughts with all of you. Thank you very much.
Thank you, sir. Thank you so much for your excellent presentation. Very, very informative presentation, sir. So now it's my job to invite our panelists to give their comments and suggestions. I now invite Professor Bhattacharjee, who has joined us just now, a couple of minutes back. Welcome, Professor Bhattacharjee, and kindly offer your comments and suggestions.
Thank you very much. Thank you, Dr. Rao. Actually, I joined, but then I was watching it all right because I had a class. So apology for that. Actually, I was taking my class and simultaneously keeping an eye on this also.
Yeah, I understand.
And I joined around 4:55 or so. Anyway,
yeah.
No, I think Ojha PN, PN Ojha, my good friend and earlier student, has made excellent presentation, done good work.
I am a student. I'm your student, sir, not on friend. So still you consider me friend, but I am your student.
All my students are my good friends.
Yeah.
Yes. Thank you.
They're my good friends. Anyway, coming back to it. This is, of course, I mean, the ultra high performance, as Dr. TV I was showing in the chat box. I mean, reactive powder concrete, it's somewhat around 35 years now, but not much you have done in India. So the effort from NCCBM, I'd say it's a very good effort actually, or also from SCRC. I attended a workshop. I mean, I was invited in a workshop in ACRC maybe a few years back when they were also looking at it. But one point Ojha mentioned is very important. It is to be, like industrialized technological precast system. You can't do it. The quality control requirement is very, very high. That is one very important point. Second aspect I see is that possibly it will come easily in infra like bridges. Bridge system, and because it's if you see the dimension of the element is as good as pre-stressed element of 200 MPa grade or anything more than 200, they call it RPC 200 MPa grade, is as good as steel section. So dimensions, material saving, there's a lot of material saving. The other point I wanted to mention was that you see, it has to be more generalized. What I find is that our concrete science and technology tend to remain, well, we have produced this much and that's, well, it has to be a generalized principle based. And that is lacking because we are not going to, for example, one of the points that made by Mr. Ojha related to CHS length, being longer in a better structure. Well, I'm not very sure. That's anybody has measured degree of polymerization of CHS, or is it a polymer at all, or it is simply a water of crystallization? So the chemist way of looking at it, I mean, not chemist way, I'll say chemistry's way of looking at it, only from the chemistry view is possibly not the best thing. Strength of materials are governed by weakest link and not by the strongest side of it. So it is the flaws in the system, like heating, perhaps. So why heating improves, one of the explanations that I read many years back was the conversion of the C3A content should be less in the cement in this one, because C3A conversion, even in a small quantity, increase in porosity and change in pore structure might bring down your strength. So heat treatment is perhaps related to that kind of thing. And I'd look at somebody like, for example, one full Carb Anderson's carb is used, but the powder technology from which CPM comes, compact powder model, name of FD Luru came in the chair. I mean, Laird, Franco de Laird, his book. So they have adopted from powder technology, some of those articles, and it's not easy to generalize because the particle sizes are, I mean, the cement, the concrete, it's particulate matter. Even if you are going to find particles only and not large quarter proportional particles, it varies so much, natural system. So these issues are there, and my point is that there has to be attempt to perhaps do a mathematical generalization as much as possible, so that if I am using, or Dr. Kantarao is using, or my good friend from CBRI, just now I saw his chat, Karade is using, it should be same. You see, the metals, they have that kind of thing. We understand the stress strain, the kind of behavior of metal, mechanical behavior of metal much better than this kind of particulate system, bonded particulate system, not bonded chemically much physically. So that's the kind of my comment. I would suggest that somebody looks more into the generalization part of it, so that it's not simply, codes, no other engineers use so much of code. Because we don't have proper understanding of the material, we tend to use code. I mean, why should physically modulus of elasticity of concrete be under root FCK? It's empirical, purely empirical. It's been seen by people and good for practice. But we should be looking into fundamentals, behavior, and that is all. But NCCBM is doing a great job. They may not be getting that much into fundamentals because they are economic, but universities, institutions, that should really look into those who are working into this, not stick to empiricity only. That's okay. That's my comment. Thank you.
Thank you, Professor Bhattacharjee. Thanks for valuable comments. Now I invite our second panelist, engineer Mayank Rawal to offer his comment.
बता रहा हूँ सर, मैं एक सेमिनार में हूँ, मैं बताता हूँ. जैसे ही खत्म होता है 5-10 मिनट में बता दूँ.
Thank you, everybody. Ojha sir, your lecture was very fantastic, very impressive, and a lot of points are covered. And Professor Bhattacharjee has given very good, in that directions. So many points have been covered. One point for fire resistance, as you said about the polypropylene fibers used and all that, is also very interesting, because once we go for a high performance or ultra high performance concrete, there we need to use some fibers, polypropylene, to improve its properties. One more important point which I want to tell you, that you need to have a grading of cement also. When we are talking of the packing density, the cement grading is also equally important to get that right workability when you are mixing. So distribution of cement particle, that also is a very important thing which I think we should consider in our research. Second thing is about the admixture, which I think you have not given much scope, but actually speaking, the admixture is the most important part in this type of concrete. Because when the water simulation is very low, you need an admixture. Yeah. When the water simulation is very low, you need an admixture. Hello, I'm audible?
No, you are audible. So, mute kijiye aap. ठीक है. Please carry on.
So, what happened that when we are using with a very low water tonne ratio, your water demand is there. The admixture, when we add, it starts absorbing immediately. So, we need to have an admixture with a higher carboxylic group, so it immediately gives water, performance or water reduction. So, here we need a special type of admixture than the conventional admixture for the ultra high performance, when we call it, and the water sim ratio is 0.17 and all that. Because here we need, not only workability, it should give a coating also on the particles, so that you can get a good flow. Because we have done with different superplasters, and we found that you need to change the molecule of the superplaster to, get the ultra high performance concrete. Thank you very much, sir.
Thank you, sir. Thank you so much. Ojha sir, you want to add something?
It's okay from my side.
Yeah. Thank you so much. Sir, there are some questions in the chat box, sir. I'll take a few of them. There is one question by Dr. Rajiv Garg, my senior colleague from CRRI. He asks, how microwave affect curing and strength in concrete for this particular type of concrete?
I have not discussed microwave curing. So I have not discussed, and I will have to go through the literature, because I have not used microwave.
Okay. Sure. Yes, sir.
I am not going to answer this.
Sir, there is one more question.
Yeah, can I just react
please.
to this? No, microwave is again heating.
Yeah.
So naturally, this is related to heating, right? So question of the rate of heating. Microwave interacts with water molecule.
Yeah, exactly.
Because it's a dipole. It is a dipole. Water is a dipole. Correct. And microwave, so as long as it's moist, it will do the heating. Perhaps, as Ojha said, you have to see and do the experiment and see, but it will have positive effect, surely. It will have positive effect. That's the feeling, of course.
Thank you, Brother. But there one more question, sir. What is the significance of increased Poisson's ratio in spite of the increase in E value?
Pardon?
What is the significance of increased Poisson's ratio in spite of increase in E value, modulus value?
Poisson's ratio is in the range of 0.2. So for this also it is in the range of less than 0.2. So it has not increased significantly.
Yeah.
There is no point of discussing.
From 0.152, it has gone to 0.17, I think, if I understand correctly.
Yes.
But normal concrete also is 0.18, 0.2 sometime.
Yes.
So it's not really very high here as he's shown.
Sir, one more thing, is this concrete pumpable? Somebody asked, Abhishek.
Yes. This concrete can be made pumpable. So it depends upon the type of placing. So Mayank Rawal can make any concrete pumpable or harsh. So Mayank Rawal is here. He can make a wonderful mixer, super plasticizer, and that will help in making this technology viable in real life situation. So we are struggling to have a very good kind of super plasticizer specific to the ultra high performance concrete, because whatever the super plasticizer which is available, that has not been made specifically for ultra high performance concrete. because this concrete gets sticky while mixing, and it affects the pumpability. So when it gets sticky, in this concrete, we need to reduce the viscosity. But in self-compacting concrete, having in the range of M35 or M40 or like that, we want to increase the viscosity. So having a combination of chemical admixture, and a person like Mayank Rawalji need to work in this, and we would like to get some input from the chemical admixture manufacturer.
I want to add something.
This is an area where the concrete, let me complete, Rawal sir. So this is an area where we need to work, because without this, we cannot produce the concrete which can satisfy the constructability requirement. So constructability requirement is very, very important, and that can be achieved only through good quality of chemical admixture to modify the properties of concrete in fresh state without affecting the concrete property is in hardened state and durability property. This is required.
I want to add something. Like when we go for a high performance concrete and we use a super plaster, you must have seen a lot of stickiness takes place because fines are more. Now here, a very important thing what I want to add you, that there is no need of adding too much of super plaster. Like as in your study, you have to use even 2% super plaster. What I believe that there is an optimum limit of a super plaster. After that, you are going to add some other materials which are low molecular weight fractions, which are working as a anti-sticking properties. So what happened? Your stickiness is reduced. You must have very, very good flow, but it is highly sticky because the water ratio is very low. So in such cases, you need to add super plaster, not very high, but after super plaster, you have to add other additive which with a low molecular weight, which gives anti-sticking property. So your concrete, becomes less sticky with the use of that, because it goes between the cement particle and the super plaster, a very small molecule particle. So it's the latest research people have done.
Actually, Rawal Sahab, it is easier to say than to do. Actually, I have discussed at that point of time also, can you provide this type of the material which can reduce the viscosity?
I'll give you, sir. I'll give you.
So at that point of time, I discussed many of the chemical admixture manufacturers.
So, but actually, you should write an official letter.
Able to give us like that.
I believe, sir, you should write an official letter so that we can take more seriously. Frankly. If you have any trouble like this, you can send us a letter. We can give, work on that. Because we have similar work.
It's not a letter. You will have to work together.
Oh, we'll do.
Yes.
Sir, are such materials available, sir? Mayank Rawalji, that anti-sticking materials? Are they available, or you have to do research for that and come out with that? What is the latest position like? Hello, sir? Mayank Rawalji?
Yes, sir.
They will have to do the customized product for this.
Okay. No, I was asking, are the materials available like anti-sticking?
Yeah, it is available with me, sir. And okay. You can wait, I'll just show for a minute. Just a minute.
No, sir. Please sit. We'll go to conclude, sir.
No. I have a specimen. I want to show him.
No. My basic question is.
It is possible to get a very high fluid material with a low stickiness.
Okay.
No, basically it's the
I'll give you, no problem, sir.
It is a grafted radical into the system or an additive?
No, it's an additive with a low molecule, which is added along with superplaster.
Okay. So it's an additive actually.
Because what I found that by adding superplaster, then certain range, it is not working. Okay. It is just we are adding. Workability is not increased, and it's on the contrary making it more sticky.
Yes.
So instead of making it more sticky, why not to add something else? So that the optimum superplaster is there and you get the flow.
Okay.
So your trouble is very soft.
No, we'll take a lecture from you. Actually, one more lecture from you, Mayank Rawalji.
Thank you.
Thank you so much.
Yes.
Sir, last question, sir. There is a question from one TB. I don't know the full name. How can we use polypropylene fibers whose high temperature resistance is very less?
No. That's for fire.
Yeah.
That melts, I have already discussed, that melts at 170 degrees centigrade approximately. So if this is used, if you are using UHPC where fire expectation is not there, it is not required. But that point has been discussed where there is a requirement against fire, there it is to be used, and it melts at 170 degrees centigrade.
Yes. Actually, no, actually the thing is that, where there's a fire scenario, the Michigan, of course, Professor Venkatesh Kudu, the team has worked onto it. In fact, they were the one. What they were finding is that you have very low porosity in this system, right? Water cement ratio is much more than 0.36. So no capillary porosity. Now what happens is, in case of fire, the chemically combined water, CSH, that's chemically combined water, right? Because capillary water will not be there. Gel water, very little would be there in this kind of a system. So this CSH, which breaks down around 200 to 400 degrees centigrade, that actually starts exerting pressure onto the system, right? So if you put polypropylene fiber or fibers of the similar kind, which will actually melt, it melts and actually makes it porous. The space occupied by this polypropylene allows the water vapor to move out, and therefore spalling of the concrete doesn't occur.
Yes. So
that's
before going to 400 degrees centigrade, where CHS is disintegrated, at 170 degrees centigrade, it melts and
Yes.
provides the passage,
Yes.
provides the access, provides the space.
Yes. For
Take care of more pressure.
Yes. And the spalling would not be there, because otherwise high performance concrete or ultra high performance concrete has excellent pore performance when exposed to temperature.
Right, yeah. Sir, Dr. Karare is asking, as for the type of aggregate, he is asking actually maximum size of aggregate. Of course, you showed that quad sand you are using actually. So, is it specifically for to give the strength or any other purpose? Quad sand you are using actually. What is the reason like?
So reduction in maximum size of aggregate to reduce the inhomogeneity across the concrete.
Right.
Because inhomogeneity in the aggregate itself, in terms of cracks and fissures and like that, the lower is the size, the lower is the inhomogeneity.
ITZ is reducing actually.
And it is evident.
No, ITZ is not reducing. ITZ is actually increasing.
Compacting
stress is reducing. Stress concentration is reducing. That's what Dr. Mr. Ojha is saying.
Correct.
Larger the aggregate size, the surface area is less for the largest particle.
Yes.
So the stress concentration actually increases,
Exactly,
and that's what creates the problem. And you get in Neville's book, Neville and Brooks' book long back. Higher the cement content, your aggregate size MSA, maximum MSA reduces down. So that's the concept, stress concentration. Ojha is saying the same thing.
Correct.
He's saying the same thing.
Thank you so much, Ojha Saab and our panelists, Professor Bhattacharjee and Mayank Rawal ji. Now, I think with this, I will conclude this webinar, and I'll hand over to our colleague, Mr. B.B. Wadhwa ji, to propose a vote of thanks. Sir, you are on mute, sir. Please unmute yourself. सर आपका वॉइस नहीं आ रहा है सर, ऑल्दो यू आर अनम्यूट.
अवेलेबल?
क्या थोड़ा वॉल्यूम बढ़ाइए, थोड़ा माइक के पास आ जाइए.
Okay. Good evening, everyone present in this webinar. Post an excellent and educated presentation by Dr. P.N. Ojha. Apart from useful comments and observations by eminent panelists, participants, it's an honor for me to express my gratitude and thanks to all of you. On behalf of ICI New Delhi Center, CE&CR and Revered Media, I extend my sincere thanks and gratitude to eminent speaker, Engineer P.N. Ojha, Joint Director and Head Construction Development and Research, NCCBM, for accepting to deliver a lecture from his busy schedule. Thank you very much, sir, for enlightening us on an interesting technological topic from high performance concrete to an ultra performance high concrete. My sincere thanks to Engineer Vinay Gupta ji President India ICI for making his kind presence from his busy schedule, giving an introductory remarks about development in ICI and inspiring and encouraging us about concrete technology. Thank you, sir. Thanks to Engineer Supradeep Dasji, Vice President ICI North, for presenting the role and activities of ICI. I also extend my thanks to our eminent panelist, Dr. B. Bhattacharjee, Professor IIT Delhi, and Engineer Mayank Rawal, Director Asian Laboratory and Co-Chairman ICI NDC, for agreeing to be part of this lecture and offering their valuable and feedbacks and comments. I express my gratitude to today's moderator, Dr. VVL Kantarao, Senior Principal Scientist, CSRIR, CRI, and Honorary Secretary ICI NDC for very well organizing the webinar. My special compliments to Engineer Rajiv Singhal, Chairman ICI NDC, and his team for their enthusiasm in organizing lectures and topics related to the latest development in concrete technology by eminent personalities and researchers. I would like to express my gratitude to all the esteemed participants in this webinar for their active participation and providing immense support and contribution to make this webinar a great success. Last but not the least, many thanks to our associate, Mr. CE&CR, and logistic partner, Mr. Revered Media Private Limited, who had been working hard for the last 2 days to make this webinar successful. Thank you everyone once again for making this great success. Thank you very much.
Thank you.
Thank you, sir.
Thank
Sir,
you.
next week we are going to have a lecture by our Vice President Supradeep Dasji on repair and rehabilitation of concrete structures. Kindly attend all of you and make it successful. Thank you so much.
Thank you. Thank you so much.
Thank you so much.